let's review what we've talked about so far in 4.9. We didn't get very far. If you'll remember on Thursday, it's been a while, I know, back almost, 12 days ago, almost 2 full weeks since we last talked about this. We covered 3.3. We went back to Chapter 3 and covered systems. If you'll remember, I showed you how to derive some systems that model, for example, the tank mixing problem where you connect 2 tanks together instead of just one. One of the problems on that review that I gave you is setting up the equations for that. But the reason to do that is that we're going to now talk about systems of differential equations for a while and look at the fact that we've got multiple dependent variables like an x and a y and a single independent variable such as t. And now we want to solve these systems. Now we are going to restrict ourselves to linear systems in the sense that there are going to be only linear relationships between the x's and y's. That is, all your dependent variables appear linearly. There's no products between the two. There's no higher powers of those. They are not inside nonlinear functions. However, the independent variable t can appear as nonlinear as we want. In fact, it could even show up in the coefficients, although that's not going to happen in this section, just to keep things simple. What we did talk about last time is rewriting the derivative in terms of this d notation, the differential operator, so that if I had, for example, x double prime plus 2x prime minus x, I was able to rewrite that as d squared minus 2d, well, it should be a minus 1, if that's minus there. Is that what? Oh, here it is. Oh, I was just doing an example of how you can manipulate those algebraically and still end up with the same operator. Down here, that's a d squared, a 2d, and a minus 1x. Okay? So we're going to use elimination to reduce a linear system to a single equation. Uh-oh, that's bad news. I don't know what that is, but I'm going to keep going. Somebody may not be able to see what's on my screen. Okay, so here was a simple differential equation that we were starting with. It was like
real jacked with black bars all over. Could you all do it? No, I already tried that.
So we're having networking issues probably in here. Not sure what would be causing that.
Well, I logged on after you already started working.
That shouldn't be a problem, but who knows? All right, I'm going to keep going because I want to get through this. I'll write big up here if you can't see. If you want to move closer, feel free to do so. Or try a different computer. Okay, so we rewrote this system, right? A dx dt equals 3y, dy dt equals 2x. We rewrote it in differential notation and got it in standard form. And by standard form, I mean all the dependent variables on one side and all the independent variables on the right-hand side. In this case, since the right-hand side is 0, what would be a good name for this kind of system? Homogeneous. When things equal 0, in the linear cases, we always refer to them as homogeneous. Okay, so we looked at this and thought to ourselves, what could we do to get rid of one of the dependent variables? That is, can I multiply or apply some operator to one, another operator to another, so that when I add them up, one of them cancels? Think of it just like algebra. Think of it as 2x2 systems. Think of it as linear algebra, where you're going to eliminate one of your variables. So what I did was I applied d so that this became a minus 3 dy, and I applied a multiplication of 3, so that now these two, whenever I would add them up, will cancel each other out. But if I apply d to the first equation, I'm going to have a d squared minus 3 dy, and then the derivative of 0 is 0. On the second equation, I'm multiplying by 3, so I have a minus 6x plus 3 dy equals 0. Okay, so the result of adding those together now gives me d squared x minus 6x, which I could then rewrite as a differential equation. Now, it's homogeneous with only one unknown. Okay, so now we're going to finish this problem. And we're going to finish it by solving this differential equation for x, and then go back and solve for y in almost the exact same way. Okay. So, x double prime minus 6x equals 0. How do we solve this homogeneous linear differential equation with constant coefficients? M squared. Yeah, it's called the characteristic polynomial.
Oh, that's the one.
Right? So M squared minus 6 equals 0 means M is, our two roots will be just plus or minus square root of 6. Okay? So, x of t, the solution for my x would be c1 e to the square root of 6t plus c2 e to the minus square root of 6t. Right? If you got two distinct roots, it's just e to the root t, e to the root t. If they were multiple roots, that's where you stick in extra t's. If they were complex roots, that's where you show the sines and cosines coming into play. Okay. So that's my x. Now, how do we find y? To solve for y, we can do one of two things. We could take this x and plug it back into one of our equations, or we could just eliminate the other variable. Either substitute and solve, or eliminate y. Oh, sorry, eliminate x's, I guess. I'm gonna do the second technique. Let's do eliminate y. So remember, my differential equation was my system, dx minus 3y equals 0, and 2x minus, was it minus? Minus 2x plus dy was equal to 0. So how would we eliminate the x from that? So multiply the first one by 2 and apply d to the second one, right? Multiply 1 by 2 and apply d to equation 2, right? This is equation 1, this is equation 2. Which means we get the system 2dx minus 6y equals 0, and we get minus 2dx plus d squared y equals 0. Add them up. D squared minus 6 applied to y equals 0. Which is the same thing as y double prime minus 6y equals 0. You don't necessarily have to rewrite it in our standard prime notation. I only do that if it's helpful to see what this differential equation represents. But the reason you don't necessarily have to is because you've got something here that is in fact exactly your characteristic polynomial, except with a d in there instead of an m, right? M squared minus 6. It just so happens in this case we get the same exact differential equation for both x and y. That's not necessarily going to happen, and you'll see more of these cases as we go. So square root of 6 and negative square root of 6. So what's y of t then?
It's the same thing as x.
Yeah. Except these constants may not necessarily be the same for the y. So we need a c3 e to the square root of 6t plus c4 e to the negative square root of 6t. Okay, so in a different color, just and you can do it in a dash. Now we've got two equations here that we claim solve the system. But by doing elimination, we have a problem. The problem has to do with the number of constants involved. Okay? Now you'll remember that whenever we solved a single equation, the number of constants that we ended up with should always be equal to the order of that differential equation. If it's a second order, we would get 2 constants. If it had been third order, 3 constants. First order, that means that whatever the highest derivative is, that's the number of parameters we end up in our family of solutions. Okay? Now in a system, that's also true, except you've got to add up the orders of the different variables. So go back to the original system, and since the x equation is a first order equation, there would be one parameter that should show up in the solution associated with the x. And then since y is also first order, there's going to be one parameter for the y. So how many parameters should we have? Just 2. How many did we end up with? 4. And because of our introducing of a new d, that is, when we apply d, we get extra parameters in our problem. So what this actually says is that this, which I'm going to label as 3 and 4, 3 and 4 do not satisfy the differential equation for all possible C1, C2, C3, and C4. There's too many parameters. Okay, just as a side note, there should only be 2, since the system is first order in x and in y. And just as a side note, if it had been like first order in x and second order in y, that would be 3 parameters. If it was third order in x and fifth order in y, it'd be 8 parameters. You just add up the orders to find out how many parameters that you need to be able to write down a general solution. So to find out which, what we've got to essentially do is plug back in and substitute. Okay? So to me, in general, this is the quickest way to get to 2 solutions, to do the elimination twice. But I'm going to have to go back in and do a substitution either way. We got to substitute 3 and 4 back into an equation in the system to find out how 2 of these parameters depend on the other 2. We should be able to reduce this down to the number of parameters that we need. Okay, so let's do that. So I'm going to take 3 and 4, I'm going to take these, and I'm going to plug them into this system here. Okay, so I'm going to take dx dt, and I'm going to take my y and plug it into this first equation right there. Okay, so if x of t is this guy, I'm going to write the equation off to the side here. dx dt was 3y, correct? So dx dt for my solution is square root of 6 c1 e to the square root of 6t. I'm just taking the derivative of this. And then minus square root of 6 c2 e to the negative square root of 6t. That's what dx dt here equals. So set that equal to 3 times y, which was c3 e to the square root of 6t plus c4 e to the negative square root of 6t. Okay? Now, stand back and look at this. For this here to be equal to this here, What has to be true about the relationship of C1, C2, C3, and C4? For those two to be equal for all t, what has to be true? You see this, right? You have the same.
C1 and C2 have to be 1/3 of C3, C4.
So this right here has to equal this right here. Agreed? Those have to be the same coefficient. So square root of 6 C1 has to equal 3 C3. And what else? This has to equal, put the 3 over here too, right? And those square root of 6 and negative square root of 6 came in through that derivative. C2 has to equal 3C4. So I would say C3 has to be square root of 6 over 3 times whatever C1 is. And C4 has to be negative square root of 6 over 3 times whatever C2 is. So my two solutions now, and these would be the general solutions, will be x of t is C1 e to the square root of 6t plus C2 e to the negative square root of 6t. And now y of t, instead of C3, I'm now going to write what C3 is in terms of C1. Square root of 6 over 3 C1 e to the square root of 6t minus square root of 6 over 3 C2 e to the negative square root of 6t. Now there are only two parameters.
Does it matter which one you solve for, C1 or C3?
No. You just substitute back in. The point is now that I've only got two parameters, right? A C1 and a C2. If I had done it the other way, I would only have C3 and C4, but in both equations, I might even relabel them when I was done as a C1 and a C2, just so that my solution has only two parameters, and it doesn't make sense to start with number 3 times 2.
We could have started with C1, and we could have solved it for C1 and C2, right?
Yes.
And we would have just used the
That's what I was explaining to Dylan. So it would just have C3s and C4s in here, and it would still be an equivalent solution. So if I had done C1 is 3 over square root of 6 C3, right?
Yeah.
Then my x of t would look like a 3 over square root of 6 C3 e to the square root of 6t plus, or minus, whatever. And so these two are equivalent families of solutions. Okay? So if I had given you an initial value problem, for example, and you go to the next step and you find the c's, then you'll get the same answer whether you plug it into this one or you plug it into the way that you did the other one. So they are essentially equivalent families. Okay. Okay. So eliminate, solve, and then substitute back in to find the relationship, to reduce the number of parameters that you have. I guess I didn't need an extra page. I'm missing a page from my handwritten notes. I wonder if I was missing it when I typed up this thing. All right, well, let's keep going then. Let's do a non-homogeneous case. I really want a better example in the middle. Oh, I'm going to keep going anyways. All right, let's do x prime minus 4x plus y double prime equals t squared, and x prime plus x plus y prime equals 0. We're going to solve by elimination. All right, first of all, rewrite it in D notation. So I'm going to take the x's, right, and rewrite those, and then take the y's and rewrite those. This becomes D minus 4 times x, or applied to x, plus D squared y equals t squared. And this becomes D plus 1 x plus dy equals 0. Okay, so how do we eliminate? Which one do you want to eliminate first? Which one's easiest? The y's. Okay. So what would you do? Negative d on equation 2. Apply negative d to 2. And add. Can y'all do that in your head, or do I need to write it out? So negative d applied to 2, I'll just come off to the side here and write out what I get. It's negative d times d plus 1x, right? Minus d squared y, and then d applied to 0. The derivative of 0 is 0. Okay, in this case, you're going to get away with that. In a minute, when we come back and need to eliminate x, we're going to have to apply something to the first equation. You got to remember, when you apply d, you're not multiplying by d, you're actually taking the derivative. So on the right-hand side, if you do something with d, you're going to actually have to take the derivative of the t squared thing. Okay, we'll see that when we get to it. Okay, now I'm going to add these up together. I'm going to get d minus 4 x minus a d times d plus 1 x. The y's drop out, equals t squared. You with me okay? I mean, again, the good news is the d's can be treated just like variables. That is, you can think of this as keeping the x factored out. This becomes d minus 4 minus d squared minus d applied to x equals t squared. Right? Just factor out the x, multiply in or distribute the d. Simplify this, you end up with minus d squared minus 4 x equals t squared. And I don't like the minus in here. I'm just going to go ahead and change that to d squared plus 4 x equals negative t squared. Just multiply both sides by negative. Okay, now, just to make sure you're familiar with what we actually have here. What we really have is x double prime plus 4x equals negative t squared. We've eliminated y. Now we have a single equation that's a second order linear differential equation with constant coefficients, but it's non-homogeneous. So now we got to remember how to solve these. This is a good lesson because this is going to be one of the things you're tested over, right? How do you solve a non-homogeneous equation? Find the homogeneous solution first, right? Right? It's the x is going to be an x sub h plus an x sub p. It's the homogeneous solution with the constants in there plus a particular solution, and you have two techniques for finding particular solutions. Method of undetermined coefficients, the guessing method, or the variation of parameters, which was the Wronskian method. Yeah, you've got some refreshing to do between now and next Tuesday. Yeah. All my videos are posted, by the way, so you can go and rewatch them if you need to. Got them up yesterday. I turned the advertising on all your videos, so it's probably not the most ethical thing to do. But who knows? Maybe you'll find just the right product you were looking for, from Google advertising. I wouldn't want to rob you of that opportunity.
Well, I'm fine with the ads, but I hate when you just see the same ad, and then like 2 videos later, the same ad, the same ad, the same ad.
And I don't add unskippable ads to my videos, which I could do, but I've decided not to do that. And I turn off the overlay ones. Those I hate. There's no good reason for an overlay on a lecture video, because it's going to get... Anyways, I should probably just turn it off. Wait till after the semester's over and then make money off of.
I run an ad block on like a lot of sites.
So it doesn't even matter.
But not on YouTube.
All right, so m squared. So we're going to do the homogeneous one first, right? Homogeneous solution. M squared plus 4 equals 0. So m is...
Oh, plus or minus 2i.
Yep. Then you have to remember that it is, when it's alpha plus beta I and alpha minus beta I, it's e to the alpha t times cosine of beta t plus sine of beta t with the c1s in there, right? So you actually end up with x sub h. Your homogeneous solution would be, in this case, you got an e to the 0t out front because there's a 0 as your alpha. Don't forget about the alpha, because most of the examples we've done have ended up being just purely imaginary, but you could very well get 1 plus or minus 2i. That would mean there's an e to the 1t out front of your cosine and sine. In this case, I can just write c1 cosine of 2t plus c2 sine of 2t. But that's not all of x. We now have to also solve for this. Now, you can do both methods. Either one will work. If you've got a good guess for the method of undetermined coefficients, you should use that one. If you can't guess the form because the right-hand side has other things besides sine, cosine, e to the power, and polynomials, then you need to use variation of parameters with the Wronskian method. Okay, so what's our, for x sub p, let's use method of undetermined coefficients, also known as the guessing method. What is x sub p going to look like?
At squared plus bt plus c.
Okay, none of these appear as components or in the family of solutions for the homogeneous case, so we should be able to get there, which means we now got to do xp prime and xp double prime to plug in to here and find the a, b, and the c that make this thing a solution to this equation. Okay, so x that's going to be 2at plus b, and then this is just 2a. So substitute those into here. You're going to get 2a plus 4 times at squared plus bt plus c equals negative t squared. So group the t squared as the t and the constant, so I've got a 4a times t squared plus 4bt plus 2a plus 4c equals negative t squared. Are you with me? Yes, sir.
2a plus 4c?
2a from here?
Okay. Is that a 2 in front of the a? Or?
Oh, did I not? I said it. I don't think I wrote it. Thank you.
Okay.
Yeah, I missed it. Should have been a 2. Maybe I didn't even say it. Maybe I'm crazy.
You said it.
I blame the stylus. Okay, so how do we get our equations to find the a, b, and c? Remember, you set these equal to the corresponding coefficients, right? This is like plus 0t, and then this plus 0. So 4a has to equal negative 1. 4b has to equal 0. And 2a plus 4c has to equal 0. Which means a is negative 1/4. B is 0. And so 2 times negative 1/4 plus 4c equals 0. That's negative 1/2. Add to the other side, you get 4c equals 1/2, or c is 1/8.
So basically, we're just going to have one problem in the test that demonstrate all of our
This
skills.
could be everything, right? All right, I have to give you 2 so you could do variation parameters on one.
Oh, you're right.
Method of undetermined coefficients on the other. Yeah, I like those tests theoretically because I can test you over everything, but it also has the problem that you make one tiny little mistake at the beginning and you miss the problem. But if I'm going to give you partial credit, I've got to work the problem from your mistake forward for everybody. So I like to do that. That's awesome. And I'm philosophically opposed to multiple choice math tests.
Who is my dog named after?
You could do true and false.
True or false.
True or false.
My wife was working on one that she was giving to her high school AP calculus class that was a true-false review. And there were like 30 questions on there. One was true.
Oh, that would suck even more.
She didn't write it. She had gotten this off of some of the curriculum that she has. Like, that's the
evil.
worst possible, most useless review I've ever heard of. You got to balance it. I mean, you're just always wrong is basically all that. Every answer on there is wrong. Okay. You got this far, so we're now x will be c1 cosine of 2t plus c2 sine of 2t minus 1/4 t squared plus 1/8. We've now found our x. We are about a third of the way done now. Because we also now have to find y. Then we have to find the relationship of our C's. By the way, how many parameters should we end up with? Just so you know. Go back to this one.
3.
Why 3?
It's
Second order in Y,
And
first order in X, so we should have 3 parameters when we're done. Okay. Now, let's eliminate Y. Step 2. I guess I should have labeled step 1. This was step 1. Eliminate Y. Actually, now we're eliminating X, right? Okay. So, now look at this guy. The one we started with. We're back up to here. Right there, right there. We want to get rid of the X and be left with only Y's. Okay? Now we got to be a little more creative than we have in the past, because when we've done linear addition and elimination in linear algebra and in even college or high school algebra, we always had just constants out in front, just numbers. Now we got these polynomial-looking things, the d minus 4 and the d plus 1. So in this case, what I'm going to do is I'm going to multiply or apply this by something and then this by something so that when I add them together, my x's cancel out. So essentially, I need a d plus 1 out in front of this, right? And a d minus 4 out in front of this. And just make one of them negative. Okay? But apply that all the way across. Okay? I'm going to come down here and write down what I just said. I'm going to do d plus 1 applied to 1. That's the first equation. And let's do minus d minus 4 applied to 2. So I'll go ahead and write out what I've got. That gives me a d plus 1 times a d minus 4 applied to x plus, right, plus, we now have a d plus 1 applied to d squared y equals, and I'm going to go ahead and write it, but in a minute I'm going to have to evaluate this. D plus 1 applied to t squared. And then I've got a minus d plus 1, now d minus 4x, because I applied the minus d minus 4 in there, plus, actually now minus d minus 4 dy, and on this side I had a 0, so it's still just 0. Messy, but pretty obvious what you choose. If there's not an easy one to eliminate, then you're basically finding that lowest common denominator, or least common multiple of the two polynomials that are there, the d plus 1 and the d minus 4. Okay, add those up, and the x's are gone. First of all, though, let's think about this guy real quick. What is d plus 1 of t squared? That's the derivative of t squared plus t squared. What's the derivative of d squared? 2t. So on the right-hand side, we actually now have 2t plus t squared, or t squared plus 2t. So add these up. I now have a d plus 1, I'll go ahead and write it out, d squared y minus d minus 4 dy equals 2t plus t squared. Okay, so let's simplify this a little bit. What all do we have times y? D cubed plus d squared minus d squared plus 4d. So d cubed plus 4dy equals t squared plus 2t. Tell you what, you finish one of these problems, you feel like you've got mad skills because so much that goes into these. I mean, you go out and celebrate. You know, you take yourself out to dinner after you just get through one of these.
Take yourself to your bed for a nice nap.
Yep. Okay, so y triple prime plus 4y prime equals t squared plus 2t. So now we have another problem to solve in the form of a linear, this time third order, but with constant coefficients, non-homogeneous. So we got to find y is equal to some y sub h plus y sub p. We're going to have to use method of undetermined coefficients again. Okay, so for the homogeneous, what's your characteristic polynomial? M cubed plus 4m equals 0. So m times m squared plus 4, you can factor that out. So far so good? So what's your y sub h look like?
C1 plus.
Careful. C, yes, but we've already got a C1 and a C2.
C3.
So C3 plus
C4 cosine 2t.
plus C5 sine of 2t. Yep. Let's use method of undetermined coefficients. Somebody snickered at my abbreviations before, so I wrote it down a little bit more this time. MOUC, method of undetermined coefficients. Y sub p, what's your guess?
Same as last time.
Is it?
Yes.
You got to match this, but what have you got to check now? Are any of these
In homogeneous.
in the homogeneous? No, no. Constant. Constant.
So add an extra t cubed.
Put a t in there. So we're actually going to use at cubed plus bt squared plus ct. If we didn't do that, we wouldn't have enough parameters to show to solve uniquely. So now we got to take this yp and plug it into this equation right there. Okay? So we need yp prime, which is 3at squared plus 2bt plus c. We need yp double prime, which is 6at plus 2b. And yp triple prime, which is 6a. Plugging it all in to here, we get 6a plus 4 times 3at squared plus 2bt plus c equals t squared plus 2t. I think I may finish this problem in less than the 4 pages I gave you. You didn't realize this was the last problem of the day.
Oh my god. No, I did not.
So, what have we got? We've got 12a t squared plus 8bt plus 6a, I said it and wrote it, plus 4c equals t squared plus 2t. Of course, there's a plus 0, so like before, I'm going to set coefficients equal to solve for A, B, and C. Just as a side note, while you're writing, I'll point this out. If you had you'd left off this extra t, notice that you wouldn't even have a t squared term in here. Right? The t squared term came from yp prime, and if you had only done at squared plus bt plus c, then you wouldn't even have a t squared. Yes, sir?
Why do you have the arrow linking the 8t cubed plus bt squared to the right-hand side?
Oh, to this whole equation.
Oh, okay.
So this word substitute, I was indicating we're going to substitute here. So you knew where that was. That's that. Once you get to this point, plug it back into the equation to find your A, B, C. Okay, so 12a equals 1, 8b equals 2, and 6a plus 4c equals 0. That will give you the particular part of that solution. So A is 1/12, B is 2/8, or 1/4. So I have 6 times 1/12 plus 4c equals 0. That's now 1/2. So 4c equals negative 1/2, or c is equal to negative 1/8. So your total y now is C3 plus C4 cosine of 2t plus C5 sine of 2t. And then your particular solution, so plus 1/12 t squared, t cubed, plus 1/4 t squared minus 1/8 t. And recall, I'm just going to write it down so we have it here. X is C1 cosine of 2t plus C2 sine of 2t plus minus 1/4 t squared plus 1/8. Beautiful. Only we're not done, right? How many parameters do we have? We got 5. We only need 3. So we need to find out how 2 of them depend on the other 3. So how do we find out how those 2 may depend on the other 3? This is the last step. Do what? Well, we've got a solution. The question is, solution to what? It goes back to, how many pages back? There we go, there's 2. It has to solve this, right? So that's what we did if I reflect back to here. What I did last to get the relationship, the dependencies of the parameters, was to substitute back into one of the equations in the original system. So that's what I'm going to do. I'm going to substitute x and y back into, say, equation 1. Actually, shouldn't matter, either equation 1 or equation 2. Use your initial system to determine your relationship between the c's. Okay? So plug solutions back into the system. Equation. Let's do the first one. Equation 1. Actually, it doesn't matter which one. So, I mean, it's only slightly less work, but this has a second derivative, this has a first derivative. Let's do the second one since it's just one less step. Simpler. Okay, so equation 2 was x prime plus x plus y prime has to equal 0. Okay, so this is what we're going to plug into. What's x prime? X prime is the derivative of the x function, so 2c1 sine the negative 2t plus 2c2 cosine of 2t, taking the derivative. Derivative of cosine is negative sine. The 2 comes from the derivative of what's inside. Derivative of sine is cosine times the 2 out front because of what's inside, minus 1/2 t. I've got x, now y prime. I need also, which is going to be C3, that goes to 0, minus 2C4 sine of 2t plus 2C5 cosine of 2t plus 1/4 t squared plus 1/2 t minus 1/8. Okay, so now let's do x prime plus x plus y prime. X prime, negative 2c1 sine 2t plus 2c2 cosine of 2t minus 1/2 t plus x from up here, c1 cosine of 2t plus c2 sine 2t minus 1/4 t squared plus 1/8. So plus y prime, negative 2c4 sine 2t plus 2c5 cosine of 2t plus 1/4 t squared plus 1/2 t minus 1/8. And all that has to equal 0. Now there are some signs here that we have done things correctly. Some clues to you that you may have done things incorrectly if this doesn't happen. What appears to happen to my polynomials? It's not luck. That's mathematics. You can quote me on that. So now let's group our sines and cosines together, because in order for this to be identically equal to 0 for all t, that means whatever's in front of the sines has to be 0, whatever's in front of the cosines has to be 0. The coefficients themselves have to be 0. Right? The only way to get a 0 function by adding a linear combination of sines and cosines is for their coefficients to be 0, because sine and cosine are linearly independent functions. So, in front of my sine of 2t, I have a minus 2c1 plus c2 minus 2c4. And in front of my cosines, I have a 2c2 plus c1 plus 2c5. Agreed? Just to emphasize the fact that for this to be 0 for all t, that means negative 2c1 plus c2 minus 2c4 has to equal 0, and 2c2 plus c1 plus 2c5 has to equal 0.
Plus C5 or minus C5?
Plus. And remember what I told you. We have 5, we only need 3, which means we need to get 2 of them written in terms of the other 3. We don't have to solve this thing uniquely for C's. We just need to take the C4 and C5, or maybe even the C1 and C2. Doesn't matter which 2, but we need to take 2 of them and solve them in terms of the other 3. Now, the easiest way to do that in this case is, let's just solve this for C4 in terms of C1 and C2. Right? Then I can go back and up here in my solution, wherever it went. Up here, I could replace C4 and C5 with something that just has C1s and C2s in it. Same thing for C5. Yeah, exactly. So
It's easier to do C1 and C2 though. You don't have fractions.
well, neater, cleaner, not easier. I mean, it's just.
You have more steps that way.
So if you do C1, you'll have a C2 on the right-hand side, right?
Yes.
And then you have a C2 down here with a C1 on the right-hand side. So you really would only have reduced your... Would you have reduced anything? Because you'd still have C1s and C2s, and then C5s and C3s, and you'd still have all of them there. So you haven't really eliminated anything by just solving this one for C1 and this one for C2. I mean, you could solve the system with substitution that way, but yeah. Negative, so move the other side, so that's positive 2C1 divided by 2 is C1. How about I do it in steps, just so that I don't make any mistakes here. Negative 2C4 is 2C1 plus C2 minus C2, which means C4 is negative C1 plus 1/2 C2. Agreed?
Mm-hmm.
And then 2C5 would be negative 2, I'll just do this in terms of C1. Negative C1 minus 2C2, which means C5 is negative 1/2 C1 minus C2. So now, your x of t will be C1 cosine of 2t plus C2 sine of 2t minus 1/4 t squared plus 1/8. And y of t will be C3 plus negative C1 plus 1/2 C2 cosine of 2t plus negative 1/2 minus C2 sine of 2t plus 1/12 t cubed plus 1/4 t squared minus 1/8 t. And since I didn't give you an initial value problem, just the differential equation, we're done.
Darn.
That's insane.
That's the longest problem I ever had to do whenever I was an undergraduate.
Take home homework.
It's only 2 pages.
Yeah, if you write neat and don't waste a lot of time writing all the extra stuff, it's not that bad. There has to be an easier way, right?
Got a Wolfram.
Well, even Wolfram doesn't do this method.
No, it's stupid hard.
Stupid long. That's all I got from this. Okay, let's talk real quick about the tests. I gave you a review. I think I printed enough for me to do this.
Or you use the computer to scratch out 2014 and put 2016.
Yeah.
Why don't you just delete it?
Because I was explaining that earlier. The software I use to write this test is the typesetting language LaTeX, and I don't have it installed on my current computer. It's where you write the whole thing in like an ASCII text notepad, and then run it through a compiler so it makes all your equations look very pretty, prettier than Word can do. And so I opened up it in a PDF and annotated it because I'm lazy. Actually, I would have. I mean, if you really want to give these back, I can give you a better copy on Thursday. That's when I was going to give it to you originally. I thought I might as well just do this. All right, so the front page, actually all the way through problem. Is it? No. 1 through 5, front page, is essentially chapter 3. It is solving or setting up your models and solving them. So equation 1 is a population model. Equation 2 is a falling body, a projectile. 3 is a 2-tank problem. 4 is Newton's law of cooling. And 5 is the logistic model equation. Okay? When you get to the back, this actually starts chapter 4. 6 has to do with just proving something is linearly independent using the Wronskian. 7 is if you had found these roots with certain multiplicities, what does the homogeneous solution look like? And then 8 through 12 is solving linear, higher order differential equations with constant coefficients. Number 10 is a method of undetermined coefficients. 11 and 12 are both variation of parameters. 13 and 14 are initial value problems like 8 through 12, but you got to go ahead and finish the problem by finding the C's. And then 15 is just a brutal method of undetermined coefficients. You don't actually have to solve it. You just have to tell me what the particular solution would look like. Turns out there's 14 undetermined coefficients if you do it right.
Question.
Yes.
Do we get some type of equation sheet?
Absolutely, yes. You should take a whole page for this test.
Oh my gosh.
Front and back or just?
Sure, front and back. I mean, all 6 sides if you want to.
There's a lot of stuff.
Yes, there is. Yes.
Are we doing like this many problems on the exam?
No.
Because it takes a lot of time.
Remember, no one of these problems. I mean, this is like 4 of these problems on one test, right? Or maybe even more than that.
Like, I don't even know why that exists.
We solved it. We now know what the solution is for this system. And all it meant that we had to do was eliminate one of the parameters and use our old techniques to solve it. Okay? We can reduce a system down by a variable by eliminating, and then all of our previous techniques apply.
What kind of system was produced, or what kind of, like,
What would be a real life thing for that?
Yeah.
Well, this is a coupled system. I mean, the tanks that we did would be a lot like this first one, in that you end up with the coupling of the system has to do with tanks exchanging their rates. So if you go back to 3.3, like I'll pull it up right here. I'm going to stop recording. You don't need all this.